Okay, welcome to lecture 5. Great. So today, what we're going to look at is another optimization method, the Newton method for optimizing loss functions in machine learning. And last week, if you guys check ML Blink 4.4, we looked at gradient descent and how we define that basically. And at the end, we will look at the major issues with the gradient descent algorithm. So you guys know now that the gradient is a vector, so a vector has a direction and a magnitude. The direction, if it is zigzagging, that's a problem in gradient descent. If the magnitude is vanishing, that's another problem. Okay, so we're going to look at both those problems in very simple way. Okay, so just to recap what we saw in the last lecture. So this is a typical formalization of a machine learning method. So what we're trying to do, we're trying to minimize a loss function. So by minimizing the loss function, we find the optimal parameters for our learner. So for example, let's say we want to do a regression. So we want to build a regression model, and what we have here in this figure, we have only one feature, right? And this is the target output. So this is basically your X, and this is your Y. And this line is actually your FW, okay? So what we want to do, we want to minimize, we want to find the best fit to the distribution of our points, of our samples. So we want to minimize this error. So it can be the distance from each point to the fit line, okay? Or the regression line. So what we're doing, we're plotting, we're changing the parameters of our model. So we're starting off probably somewhere, let's say right here. Okay, and there are two parameters in this case to estimate for the regression. We're going to look at this in more details in the next lectures, but just to give you an example, what we have two parameters. The first one is what we call the intercept right here, and the slope. Okay, so the intercept, you can look at it as your W1. This is your first parameter, W is your first parameter, and the second parameter, W1. Okay. So let's say we start off at this point. So this is our initial guess. So it's like superscript 0. So what you see when when we're having when we're plotting our cost function, we haven't reached the minimum. So our initial guess is not a good guess. So you can see the loss is still quite high. How do you know that? You look at this, and you can see that your points are far away from your learner, right? Your line, the parameters of the line that you learned, W0 and W1, the intercept and the slope. Okay? So in the second case, once we find the optimum, okay, right here, we find the best slope and the best intercept. So these are this is our optimal point, our W star, right? So f of W star we can see it's a very good fit to our data. So the regression works very well because it minimizes the error between the observations and the fit line. Okay, so this is, for example, how we can formalize a machine learning problem we write it as a loss function that we want to minimize. And let's look at another case. Like, for example, for classification, right? So what we want to classify the blue dots and the red dots. And in this example, we have two features. We have feature 1 and feature 2, right? So in our space, let's say we designed those features or we extracted them. So all of our samples, they belong to R2. And then what we want to do is same thing. We want to find the parameters of this linear classifier, right? So it has two parameters, same thing, intercept and slope, but we want to know where exactly to plot that line in such a way that we're maximizing the margin or the distance between these two classes. So if we start right here, you can see that for this initial guess, we have FW0, right? We don't have a very good classification because our classifier is making many mistakes, right? So what we want to do, we want to minimize the number of mistakes we're making. We want to minimize the error, right, between the predicted label and the ground truth label. So here, the predicted label, according to this classifier, these guys are blue dots. So it sees them as blue dots, but they're not blue dots, right? So these are mistakes. Now, if we look, when we optimize our function, we do all the derivation, the gradient descent, we do our nice walk, from here down to the optimum, we found the parameters of our classifier or of our line, the intercept and the slope. Then you can see we have a very nice separation between the red dots and the blue dots. Okay, so this is quite simple, especially when we're using linear models. Great. So just also to remind you, what we looked at in the previous lecture is like for a univariate loss function, which means we have a single parameter, it's a scalar. We plot our loss function. We might have, we look at the first derivative. So the stationary points, these are points, well, the first derivative of the function nullifies, so we find it can be a saddle point, it can be a global minimum, it can be a maximum, a local minimum, right? And then also for the multivariate loss function, so in a high dimensional space, we looked at the same problem. So instead, in this case, we have a quadratic form. To know if we have a minimum or not, we look at the eigenvalues of the Hessian matrix. This is our Hessian matrix, and you can see, we have a very nice convex function when they're both positive, and here they're negative, so this is not convex, okay? Right, and here we know that if we want to find the minimum, we need to look, the second derivative should be positive. Okay, so that's our minimum, and here too. So second derivative is positive. Great. Now, this is the algorithm for the gradient descent, and we can use it on any function, right? Whether it's a univariate loss function, multivariate, we can apply it as long as the function is differentiable. We can compute its partial derivative. Then we can apply our algorithm. So first we need to have, so the algorithm actually have three different parameters. So the first one is the step length, the alpha. We need to specify the initial point where we're starting off at, so the W0, and also we have the epsilon, right? For example, 10 to the power minus 3. So the epsilon is the stopping condition where the norm of the gradient should be smaller than epsilon, so which means it's very close to 0. That's our stopping condition, and this is the update rule, how we slowly walk, from the initial point downward to the optimum to minimize our loss function, okay? So once the gradient is almost flat, so it started off like, we have like a large slope, but once it becomes flat, close to 0, then we know that we are at the minimum. Great, so today we're going to look at more examples quickly. So here is a plot of a function, so log 1 plus exponential w squared, and there is a nice application online, and you guys can use it if you just want. If you're lazy to do the maths, but it's better to do the math by yourselves. So if you check derivative calculator -calculator.net, you can just type in the function, then easily derive its roots, and you can also compute its derivative, and this is the derivative of our function right there, and you can find where the derivative takes 0 values. Okay, so as you guys can see here, we computed the derivative. This is to run the gradient descent algorithm. We need to compute the derivative. In this case, it is explicit. We have the alpha. We have also our initial point, W0, right here, equals 1. And our epsilon, our stopping condition. We run the algorithm. So I gave you the demo last time in MATLAB. So we start at 0, next point, the gradient descent will jump right there to this point, then 2, and then it slows down and crawls as it converges to the minimum. So it converges after 15 steps. And I would like you guys to keep this in mind, okay, for this function. Right, let's look at another example. Now, it's a high-dimensional loss function. So here it's just 2 dimensions. So we have 2 dimensions. So W belongs to R squared. And this is our function. It's in the function of cosine. So cosine to pi WT transpose W, that's a dot product, and also 2 WTW. And this is actually the gradient. You can easily compute it using the formula of linear algebra. We can derive it. So all you guys need to care about for now is understanding those, is learning how to interpret loss functions, understanding how to run algorithms. But you don't really need to derive all the math, but it will be good if you look at the matrix cookbook I attach and you look at those, like formula, and try to find the one that blends into your case and derive the math. That's a good exercise, okay? So here, let's look at this case. So we have 2 initial points. So the first point, our first initial W0 is located right here. So you can see that the gradient is jumping and then crawling a little bit right there, and it's converging to the optimum in red, the red point. But did we find a good optimum right here, a good minimum? No, it's a local, right? So our initialization rate for this non-convex function has led us to a local optimum, which means our classifier, the line, will not be a good fit, right? If it's a regression, for example, or a good split between 2 classes, it will make a lot of mistakes. Now, if we start off right here with this initial guess, right? So these are the coordinates of our initial guess. Then we can see we nicely converge to the real minimum. And in this case, our classifier or regressor will have a very good performance, which means the error will be very low, right? Okay, so with these 2 initial guesses, you can see we have a local minimum. So this is not good, but with this one, we have a global minimum. So these are problems you guys need to think about when you have a non-convex function. Yes?
How do we know if we have a good result once the algorithm converges?
So this is a very good question. How do you know that we are stuck at a local minimum or not? So can you think about a solution?
You can test and see if your test results are good, and they're not tried, but I don't know, is that too cumbersome?
Right, so that's one of the things we can do. We can randomly sample different initial points, right? And run them in parallel. If you're using parallel computing, right? So because gradient descent will take some time, right? So you can have many, randomly select different initial points, and then you will know that you are hopefully at a global minimum if your loss is the lowest, right? So you will pick your initial guess that gave you the lowest cost function, it lowered it. But the problem is that there are many strategies, but this is one of the naive approaches, starting with different initial guesses and then running the algorithm. And the easiest way is say, okay, I know that here my loss is, for example, my loss at this W0 is equal to, I don't know, maybe equal to 2, right? But my loss at this W0 is equal to 1. So this is a better choice, okay? So you know that's a better potential solution because it minimizes your loss better, okay? Great. So now let's look at the second method, Newton's method for minimizing the loss function. So this is also a very basic technique in finding the minimum of our optimization function. So what do we use for this one? If you guys remember, for the first one, for the gradient descent, we use the first order Taylor approximation of our function. We use the gradient, right? And we approximated our function by using the negative. We performed the gradient descent or the optimization by following the direction of the negative of the gradient vector, right? Now in this case, what we will use the second order quadratic approximation to locate the optimum W star of our loss function L of W. Okay, so what are the steps? The steps are quite simple. So I would like you to look at this and understand, and also try to remember, envision it, see how it works. So let's start with, let's say we're starting off at this point. This is our W0. Then what we do, it's a simple thing. We approximate the curvature of our loss function. So we compute, if you remember, guys, the second order approximation function of our target general function L. So this is, this function locally approximate the L of W around W0. Okay, so it's a local approximation. So before, what did we have? We have our first order local approximation. It was the tangent. Now it's a quadratic. It's a whole like function, like quadratic function that we're fitting to approximate locally how our loss function looks like, its curvature. Okay, so once we find that, what we do is quite simple. So let me draw it again. So we find its approximation at W0. Then we travel to a stationary point of that function. So let's say a stationary point here. What is it? It's a minimum in this case. Okay. So the stationary point, it's where our function is equal to 0, right? So we're looking to find this point. So this is our next guess. We halt at this point, and then what we do is exactly the same step. So we hop back onto the loss function. We find this point, right? And then we approximate it again locally by a quadratic function. And then we travel from this point W1 to a stationary point right here of this function. And this is our W2. And we do the same thing. So next we need to hop back on to the function right here, find our point. So this is L of W2. We approximate it locally using a quadratic function, and continue and do the same over and over again. So you guys can see how it works, okay? Great. So what I would like you to do is I would like you to think about the maths. So I will give you 2 minutes and try to derive the update rule for this algorithm, for Newton algorithm. So you remember before, when we looked at the gradient, so we just wanted the gradient to be equal to 0, but in this case what we're looking for, how do we find this W? So I'll give you a hint. So this W is where the second order approximation of the loss function H is equal to 0, okay? So it's the gradient. The gradient of that function in high dimensional space is equal to 0. So if we solve this, if we compute the local approximation, this is, just the Taylor function. You remember it, guys, right? So it's like you're approximating it. So we wrote it before. It's the second order approximation of the loss function L of W around a point W0 if we start off at that point, right? And then what we need to do after we plot this function, this quadratic approximation, we need to find its minimum. So we need to solve this problem, okay? So just think about it. Even if you cannot recall the full, like the formula, think about it. Think about how to solve it. I'll give you 1 minute, okay? You can look at your notes. You can find in your notes probably this formula. If you find it, it's easy to derive. It's not difficult. So the first one, when you're moving downward, you're following a line. But in this case, what are you following? A curve, right? These ideas are quite simple. You can see how, like the people like who came up with them. Those concepts all derived from intuitions from calculus, right? Okay, so let's look at this case. So before I give you the answer, let's say we're using Newton's method to find the minimum for this loss function, right? So if we start off at this point, so we'll have two initial guesses. W0 and another W0 right here. So we're fitting a curve, right? So quadratically approximating the curvature. So since this is convex, it has a positive curvature, so the approximation should also have a positive curvature, right? So it looks, it faces upward. And then what we're going to do, same thing, we're finding the optimum of our quadratic form. Next point, hopping on, approximating again. And we will ultimately find the optimum right here. Now, if we start at the second initial point, W0, then you guys notice that this curvature, it's a concave part of the function, right? So its curvature is negative, so the local approximation, the approximating function, its curvature cannot face forward, right? It can be like that. So to approximate it, it will be something like this, okay? So now the problem is, in this case, we want to travel from this point along the curve to meet a stationary point of this quadratic form. So what is a stationary point right here? It's a maximum, right? So yeah, so we travel to the right, find the maximum where the gradient is equal to 0, and this is our next point, W1. And then we do the same, we hop back onto the function, right? Compute the approximation right there. And then move to the maximum. So what do you guys notice? Are we performing a gradient descent? No, we're performing an ascent, right? So we're climbing, we're not minimizing our loss, we're maximizing our loss. So this is not a good thing. So you can see that Newton's method, if you have non-convex function and you start off in a concave part of the function, it will not go well, okay? So here are the cases. So let's look at this closely. So what do we have? We have two examples. In the convex, if we have a nice convex function, then you can see that very nicely we're jumping from point to point while minimizing the loss. So the loss is getting minimized. Whereas in the case where we have a non-convex function, so in this case, come on, go. So in the case where we have a non-convex function, you can see that in the concave parts, it's not very, it doesn't go downward, it goes upward, so it's climbing, and this is not actually a good case, okay? So this is quite stuck, so I guess I need to exit and get that. Okay, cool. Now let's look at the maths. So how do we do this? So this is the second order Taylor approximation of our function at around a point W0. So this quadratic approximation is only valid locally. This is why we call it a local approximation. So in gradient descent generally, if you guys look, the thing is, in this case, you can plot the whole function. It's so nice. You can see how it looks like. You can find the minimum. But in real machine learning minimization or optimization problem, you cannot visualize the high dimensional loss function, right? With all your variables, you don't know how it looks like. It's very hard to visualize it and plot it. So when you're moving, all you can see is your local neighborhood. All you can know and rely on is your, like, basically your neighboring points, your buddies. Like you're just looking at that and then slowly trying to learn how to navigate along the right direction from part to part. So the problem here is that ideally you would look at the whole function, have a global view, and then say, I know where the minimum is, I can just go right there, right? Or you can, as you mentioned last time, you can explicitly derive it, but generally you don't have a closed form. You cannot plot your function, your high dimensional function. So you need to look locally, and to look locally in maths, it's just, you're just using a Taylor approximation. So you're using the gradient, the tangent, and the approximating quadratic form, the curvature. And from there, by looking at what's happening here, you learn in which direction you can move, right, to minimize your loss, and hopefully slowly, stucky, not good. Okay, come on. Every time I try to zoom on that figure, it gets stuck. ML5. Okay. So yeah, so you can see, I'm not going to zoom again, I'm done. Okay, cool, so you guys can see what's going on. Now let's look at the math. So here, this is the second order Taylor approximation. So this is, just the gradient, what we looked at before. So, WK equals WK minus 1, but in our case, we take the negative of the gradient, so it's minus alpha the gradient. And here we add the second order approximation. So what we need to do is we need to compute the approximating quadratic function, and set its gradient to 0. And this is exactly what we're doing right here. We're setting its gradient to 0 and solving the system. So what do we get? So if we move things around, if we simply move things around, we expand this multiplication, right, and move things around a bit, we will have these guys like going right here, okay? And the other term, and the rest is equal to 0. So it's quite simple. You can see I've just expanded that. I've done nothing complicated. And this form is quite interesting because you have a constant right there that depends on W0, your initial guess, initial point. Another constant right here, and another one right there. So this constant, we can call it B. The first one, this is a matrix. It's the Hessian matrix, right? So it's a matrix A. And we have our variable. This is our next guess. This is the optimum that we're looking for. So the Hessian matrix, if we are in Rn, then its dimension is n by n. Then why this is a vector? So the gradient is a vector, so we know that the gradient belongs to Rn. And what about this? It's, we're multiplying what? A matrix, which is like n times n, right? By what? Why this is a vector? It's just a multiplication of a matrix and a vector, right? W0, remember, W0 is a vector here, right? It has many, it's just initial guess, but it has many values. It can be 2 features, 3 features, 1,000 of features, okay? So what we need to do to find our W, just solve this system of linear and nonlinear equations, and we find our W, okay? All of its coordinates in all n directions. That's it. So that's all we need to do. So you guys don't need to derive the math, but you need to know that this is what we're solving in Newton's method. Now, once we find the solution, then we travel. So let's say we calculated, we found our W1 by solving these equations. Then what we do, we're going to repeat that many times. So every time we solve this for W2 and put W1 right here. Okay, so that's our next point. And we repeat this over until convergence. So what is the stopping condition? When do we know that our algorithm has converged? When the gradient of the loss is close to 0. Same stopping condition as for for gradient descent methods. Okay, so looking at this, at the kth step, we're estimating WK, right? So we solved for this one. So what happens when the gradient is equal to 0? The gradient vector. So if you replace that, what do you guys find out? Yes, very good. It's a fixed stable point. So WK will be equal WK minus 1, right? Because this is equal to 0, these guys are the same. So these points should be equal, right? So you have like you found your optimum, right? You're not moving anymore. You're stopping because your gradient is very close. So here it's equal to 0, but in reality, in your numerical methods, it will be close to 0, like 0.0001, for example. Okay, cool. So this is Newton's method, right? So this is the algorithm. So given a twice differentiable function L, our loss function here, an initial point W0, we start off using K, we initialize K using 1. And what we'll do, we'll solve the system. So it's a whole system that we're solving right here. Okay? And we're solving for WK. So we want to estimate the WK, right, from the previous point. And we're going to repeat this. So it's the same thing. Okay? Now, what happens if the Hessian matrix at point WK minus 1 is invertible? How can we write this? So I would like you guys to try to write this down. Okay, I'll give you 2 minutes and replace it. So what does it mean that the Hessian is invertible? Invertible, it means we can inverse it. Okay, so it means this basically exists, right? So we know that we do x times x, the inverse of x, we have 1, right? So I would like you to apply this rule and find the new formula, the new update for the WK. So what do you guys get? It's quite easy, right? So if you multiply by the inverse of the Hessian matrix, so here this quantity will be equal to 1, so we multiply the left side, right? So because we are applying this rule, so it's just, we're multiplying x and x inverse, like so 1. So that will gives us WK, and then here it also disappears, so we have WK minus 1. Minus what? We need to multiply the inverse of the Hessian matrix right here by the gradient. So what do you guys see? What does this remind you of? Gradient descent, very good. But in this case, the inverse of the Hessian, it replaces the alpha. So this is a good thing because previously we needed to tune the alpha. Remember when it's too large, we might overshoot the minimum. When it's too small, it might not ever converge. But in this case, when you're using Newton method, you're free of this parameter alpha that you don't need to tune it anymore. Okay, so you can compute the inverse of the Hessian, then you can solve the problem easily. So let's now compare these two. just to quickly wrap up this part. So what do we have? We've seen the gradient descent. So this is exactly the same algorithm initialized at the same point, W0 equals 1. And you can see that we have, when using gradient descent, the algorithm converges in 15 steps, while when using Newton, this actually just 3 steps, okay? So one important thing, one advantage of using Newton method is if your loss function, if L is convex, then it converges much faster than the gradient descent, okay? Because it's just jumping using this, by following the curve, right? Now, what else? What another advantage of Newton's method? No alpha, so we don't have an extra parameter, as in the gradient descent. What are the pros of this method? Disadvantages of Newton. If it's concave, right? If it's a non-convex, so if it's a non-convex function, then it might not converge. So this is a problem. Another one, if you are using the inverse of the Hessian matrix, if you're not solving the n linear equations, then you inverting the Hessian matrix might be computationally expensive, because imagine that you need to store, for example, 10K parameters. You have like 10K features, and you need to create a 10K times 10K matrix, store it and invert it. That is very computationally expensive and memory expensive, okay? But if you're opting for solving the set of n linear equations, that's much faster. Okay, great. Now let's look at examples. So this is the example we saw before, but now what we're computing is the second derivative. And here we notice that the second derivative is always positive. It never takes, it's all exponentials basically, so it's always positive and strictly positive, which means we can easily invert it. So here, this is the gradient descent, and our alpha is 1 divided by the second derivative, okay? So it's the inverse of the second derivative, and you can see it nicely converges in just 3 jumps or 3 strides. Now for this case, this is another case. What do we have here? We have our initial point. So this is a quadratic function. We've seen this before a few times. We've seen it in base classifier when we talked about the data distribution, right? But now we're seeing it as a loss function. So we're using quadratic forms for a different purpose. So in this case, we take R is like a unit vector, D is equals to 0, and we predefine or prefix the Q matrix and define and plot the quadratic loss function. So this is, L of W, and you can see how it looks like right here. So this is our initial point at 10, 10. Let me use another color. So this is our initial point, and we compute the derivative, right, and the Hessian. So I would like you guys to apply the update rule and compute W1 and W2, like write it down using this formula, okay, especially those, right? So replace the Hessian, replace the gradient, and tell me what do you guys find out starting from W0. So I'll give you 1 minute, okay? So your K here, you'll start off, K equals to 1. Yes. Same. So it's not getting.
You write wrong.
I did wrong. What did I write? Sorry.
Second W should be W0.
W0.
K.
Oh, yes. Thank you. Yes. Yes. No, actually, when k is equal to 1, we start off at W0, so this should be 1. Right? Is that what you meant? Actually, how I wrote it was correct. Because k equals to 1. So k minus 1 is W0. Right? So this is actually this guy. And this is this guy. K equals 1. Right. Yes, you're right. It's the second one. That was I correct, but it's the second one. Thank you. You're right. Yes. Okay, so what do you guys find? So first, the first one, this is a constant, right? The Hessian. So it's just Q. It's right here. It doesn't depend on the W, right? Doesn't depend on the W. And the second one also, it's Q. And here, what do we have? If we replace the gradient, so we have QW0 minus QW0 minus R. Okay? So now these terms are equal. So what do we have then? We have QW1 equals minus R. Then, if Q is invertible, in this case it is, so it's equal minus Q inverted times R. Okay? So then if we compute also W2, what do you guys notice? It's exactly the same point. So we have converged only in a single one jump, one step. That's it. So it's a constant, right? Great. So yeah, so this is, these are the formula that we learned in gradient descent, so the update rule. And also for Newton's method, so if the Hessian is not invertible, you write it this way using the second order approximation or optimization. And if it is invertible, if the Hessian matrix is invertible, then you can write it this way. Okay? And now I'm going to give you a demo in MATLAB. You guys can look at this. It's in the Machine Learning Refined exercise 2.14.